Hello students, welcome back to my YouTube channel. Today we are discussing another previous year question from the JEE Advanced. This question is from JEE Advanced 2018 paper 2. It is also a question on the electric flux. This is rather a slightly easier question. So we will see how to solve this question quickly. And then we will also see a slightly harder variety of this question today. So let me read out the question. The question says, an infinitely long, thin non-conducting wire is parallel to the z-axis and carries a uniform linear charge density of lambda. It pierces a thin non-conducting spherical shell of radius r in such a way that PQ subtends an angle 120 degree at the center O of the spherical shell, as shown in the figure. The permittivity of free space is epsilon naught. Which of the following statements is or are true? So we need to find out the electric flux through the shell, and also we need to check what the z component of electric field will be. Will it be non-zero, or will it be zero, or will it be normal to the surface of the shell at all points? Great. Let's get into the question. We'll start with the key ideas that are very useful in this question. The very first key idea is the Gauss Law itself, which states that the net electric flux through any closed surface is just 1 by epsilon naught times the total charge enclosed by the Gaussian surface. So basically in this question, if somehow I am able to identify what is the total amount of charge enclosed by the spherical non-conducting surface, I will be able to find out the total flux through that surface. The second key idea that we are going to use is how do the field lines due to an infinite line charge look. For example, let us consider these two elements over here on the infinite line charge. If you look at the electric field due to them, let us say the lower element 2 produces E2 over here and the upper element 1 produces E1 over here. Now since we have chosen symmetric elements, these elements produce equal electric field. We see that the vertical components of E1 and E2 cancel out, whereas the horizontal components of E1 and E2 get added. So therefore, in case of an infinite line charge, you will have electric field lines actually spreading cylindrically, radially outward from the line charge. As you can see, I have shown an example over here on the right diagram. So the electric field lines due to infinite line charge go radially outward and they spread out in a cylindrical fashion. Okay. So these are the important two key ideas that we need to solve this particular question. Now let us dive into the solution. So here I have made a diagram of the given question again over here. So what we see is from the figure, the length L of the wire that is inside the non-conducting sphere is going to be r sine theta plus r sine theta, where this is the radius of the non-conducting sphere, which is equal to root 3r. So basically, the length of the non-conducting wire having uniform charge density lambda inside the spherical surface is root 3r, which basically tells you the total charge enclosed by the surface is going to be lambda times the length, which will be root 3 lambda r, which basically through Gauss law will give us that the flux through the closed Gaussian surface or closed non-conducting sphere that we have over here will be root 3 lambda r divided by epsilon naught. So it's very direct. This question is not exactly very difficult. If you are able to find out how much charge is enclosed by the non-conducting sphere, very easily you can find out the net flux through the sphere. And we have already seen the electric field due to the infinite line charge is going to spread radially outward in a cylindrical fashion, which indicates there will be no component of electric field along the length of the line charge, right? So here if we draw the diagram, all the electric field will be spreading radially outward over here. So you are hardly going to have any components of electric field along the z direction, because the z direction is along the length of the wire, correct? This is the z direction. So you will not have any electric field along the z direction. So therefore we can say very simply that option A is correct, and other than option A, we can say that option B is also correct, right? So we can say option B is also correct. So which basically tells us the answer for this question is going to be A and B. Now we are going to see another question which is a modified version of this question. I have made it a slightly harder question, and let's just see how to solve that one. So now we are solving this new modified version of the same question. Let us read it out. An infinite long thin non-conducting wire is positioned parallel to the z-axis, and it intersects the xy plane at the point r by 2, 0. A fixed spherical shell of radius r is centered at the origin O of 0, 0, 0. Unlike the standard case, the wire possesses a non-uniform linear charge density. So this wire does not have a uniform linear charge density, it has a non-uniform linear charge density, which already makes the question slightly difficult, because it's not just enough to find the length of the wire that is inside the sphere now. Let's continue the question, where z is the coordinate along the length of the wire. Z equal to 0 corresponds to the point closest to the origin, and lambda naught is a positive constant. So we now need to calculate the total flux through the spherical shell. So we have 4 options and we need to verify which of these 4 options are correct. So I have included the diagram for this particular question for the benefit of students. We can see you have the red line is the non-uniform linear charge, infinite line charge, and it is at a distance of r by 2. It's parallel to the z-axis, and now we need to solve the question. So obviously here, since the linear charge density of the infinite wire varies along the length of the wire, thus we need to integrate in order to obtain the charge enclosed. The strategy is still to get the charge enclosed and apply Gauss law, but to get the charge enclosed we now need to integrate. And in order to integrate, we need to find the upper and lower limits of integration. Obviously the wire intersects the xy plane at r by 2, 0. That means throughout the y coordinate is going to be 0 itself, and the x coordinate is going to be r by 2 itself, because it's a wire parallel to the z axis. So of course its z coordinate will vary from sub minus z naught to plus z naught. Our first challenge is to find z naught, but that's not exactly a big challenge, because the point of intersection with the sphere can be easily found by substituting these coordinates into the equation of the sphere, which is x square plus y square plus z square is equal to r square. By doing that, we get z naught as plus root 3 r by 2, which means minus z naught is minus root 3 r by 2. So we need to integrate from minus root 3 by 2 r to plus root 3 by 2 r. I'm very sorry, I think I missed up r over here. So it's root 3 r by 2. So now we are going to integrate from minus z naught to plus z naught lambda z dz in order to get the total charge enclosed. So while integrating, we can substitute the value of lambda z. Once we substitute the value of lambda z, we realize that this integration is not exactly very difficult. First of all, lambda z is an even function. Since it's an even function, we need not integrate it from minus z naught to z naught. We can only integrate it from 0 to z naught and multiply it by 2. It's very easy. Now 2 lambda naught r has come out of integration. This is because it's a constant, And this is a standard integral. We have a direct formula for this integral dz divided by root of z square plus r square, which is ln of z plus root of z square plus r square. The limits being from 0 to z naught. All we need to do is now substitute upper limit minus lower limit. On the lower limit, only an r survives. So log b minus log a is log b by a. And we will get this. Now all we need to do is substitute the value of z naught. Z naught is root 3 r by 2. When we substitute the value of z naught into this, you are going to obtain 2 lambda naught r ln of root 3 plus root 7 by 2. Now of course, by properties of logarithm, we know the 2 can be sent into the power. And when we send the 2 into power, you get lambda naught r ln of root 3 plus root 7 by 2 whole square. And you can square it, and after squaring you will get lambda naught r ln of 5 plus root 2 divided by 2. Now many students only tick option A over here, which is fine, but actually if you will check mathematically, option 4 is also correct. Why option 4 is correct? Because if we rationalize this, we are going to get this. By rationalize, I mean if you multiply by root 7 plus root 3 divided by root 7 plus root 3, you are going to essentially get option 1 itself. Therefore, both option 1 and 4 are correct. So this is a slightly harder variety of the same question, because here you could not just find the length of the wire which is inside the sphere. That would not be enough because the charge density is variable, and therefore you would also have to integrate the linear charge density in order to find the total charge enclosed.